All right, so on Thursday, losing track of time now. So on Thursday's class, we talked about parametric equations. And we looked at how parametric equations use the x and the y coordinate with the parameter of t. Tonight, we're going to start looking at what's known as polar coordinates. And as you can see on the screen, polar coordinates are a circular graph, basically. You can take these and change them to Cartesian planes or points, which we're going to look at as well to be able to go back and forth between them. But they're really designed to be graphed on a circular polar coordinate plane. Instead of having an x and a y coordinate, we have an r and a theta coordinate. The r is my radius. So we have an r and a theta. So that's the radius. And then that's the angle. So for the first one, where we have 1 and 5 pi over 4, I'm going to go out 1 and I'm going to go to 5 pi over 4, which is not on my graph. Okay, so 5 pi over 4 is going to be about right here. So you're not drawing the line to it. I'm going to put it so you can see where it is, but you typically do not draw the line.
Professor, real quick.
Yep. Go ahead.
Is this similar to how they figure out positional points with on mapping?
Yeah.
Okay, I know about that, so I was just asking if it's related, just so I can have something related to.
Absolutely, yeah. So you're looking at your compass coordinate and then your distance from that point. So yeah, pretty much the same type of concept.
Yeah, because radius would just be the differential, and the compass point would develop the angle based off the differential, right?
Exactly. Yep.
Thank you.
No problem. So we've got that point there. So when we're looking at it, we're always starting off at the 0. The only major change between compass is normally compass looks at north is 0, where my coordinate plane, the 0 is left and right.
Yeah. When you do nautical stuff, 0 is your origin point.
Okay.
Yeah, so it's a little different. So I know what you're talking about.
So we're starting off there and we're moving around to the 5 pi over 4. So that's why that angle is over there. So that's where that point is. If we're looking at point 2 and 3 pi, we're going to go out 2 and then 3 pi. So 2 pi is around once, and then I go 1 more pi. So I'm going to be right here. So now you can start to see how that point right there, that is 2, 3 pi, but it's also just 2 pi. Those points are the exact same point. So that's one of those strange things about polar coordinates is where, since we're going basically around in a circle, you can have 2 points with the exact same value, where you would not see that on a typical Cartesian plane.
Does that mean that when we're working with these types of coordinates that we're going to bound everything to 2, 0, and 2 pi?
Yeah, so you're going to bound it to whatever you're looking at. So this way you don't have that rotation. And actually, depending on when you're looking at this, if you're going even further dealing with this, if you're looking at intersection points and it's rotating, the intersection point will continue happening because it keeps rotating. So your actual intersection point is an infinite value of points, but based on a coordinate. Like this one, it would be pi plus 2k, or actually, sorry, yeah, pi plus, or pi times 2k plus 1, basically. And that would give you every rotation of it. So it's pi works, 3 pi works, 5 pi works, 7 pi work, 8 or 9 pi will work. It's all the odd pi's.
Well, you just said struck a memory. So in pre-calculus, we talked about something to do with K, and I think it related to sine, cosine, and tangent.
Yep. When you were looking for the points that give you a specific value. And it was, they basically, you ended up going all the way out to infinity, and that was where they looked at the K. So yeah, you saw that in pre-calc.
Okay, thanks.
No problem. All right, so now we did that one. So then you look at the next two have some negatives in there. And the first two are only positive. So the negatives actually work kind of the same way, except we're going opposite directions. So when we're looking at 2 and negative pi or 2 pi over 3. So for negatives, I'm going to go the other direction. So we're going to go negative 2 pi over 3, which is going to go over here, and it's at 2. So that point's right there. So when we're looking at this one, this way, that's the negative 2 pi over 3. Which would be the exact same as going this way by 4 pi over 3. So the negative values also have a positive one going along with it. They'll end up in the exact same spot. All right, now let's look at so that was the negative angle. We would just go the opposite direction. The negative radius actually is a little crazier. So the negative radius, so I'm going to we'll start off there, and we're going to go 3 pi over 4, which means I'm going to about there. Now, here's where the crazy thing, so 3, if it was a positive 3, we'd be going, yeah, right between those two. So positive 3 is going to be 1, 2, 3 right there. So negative 3 is actually in the exact same spot on the opposite side. So that point right there is the negative 3 pi over 4. So that line basically goes the other direction, and that's where you're going to get your negative radius. So you can have, all the symbols work, but even these, it's like when you look at that point right there is really the same thing as saying 3 and 7 pi over 4. So it's the exact same. There's multiple ways to represent those points when you're going around the circle. Any questions on how to plot the coordinate plane or polar coordinates before we move on to translating them back and forth? I'm going to put, since I'll post these notes afterwards. I'll get these. See what they look like. So those are just the same representations. They just didn't do them on a coordinate or a polar coordinate graph. All right. So the next thing we're going to look at is being able to convert back and forth between the two. And it literally goes back to a right triangle. So if we're looking at this information or a right triangle, my polar coordinate is giving me my theta, which is the angle, and my radius. If I want to convert this back to the x and the y coordinate, I'm going to use the information that I know. I know that cosine of theta is adjacent over radius, or adjacent over hypotenuse. So that's adjacent, that's hypotenuse. So if I was to solve this for x, x equals r cosine of theta. So when I'm going to take my point and convert it back into a X and Y coordinate, I would plug into that, and that would give me my XY coordinate or my X coordinate. My Y coordinate is going to use sine. So same concept. I'm going to take the R over. So Y is R sine theta. So that'll give me my 2 points to find the X and the Y on the Cartesian plane or the Cartesian coordinate system. From this, we also can go the other direction. So using this right here is just Pythagorean theorem, r squared equals x squared plus y squared. So if I know X and Y, I can find out the R. And using tangent with the Y and the X, I can find out the theta. I would just do the arctangent of that, and that would give me the angle of it. And we're going to do a couple of examples of each of those. So these formulas just allow us basically to transfer back and forth between the two. All right, so let's look at this one first. We're going to take 2 and pi over 3, and we're going to change it to the X and the Y. So my R is 2, and my theta is pi over 3. So remember now, X was R times cosine of theta. So that's 2 times cosine of pi over 3. So what was the cosine of pi over 3? Anybody remember the unit circles? So if we go back to the unit circle, this right here, remember cosine starts off at basically the 1 and then goes down. So it's starting off at the 1 at the 0, and then it's square root of 3 over 2, 1/2, and then 0. And sine does the opposite. Sine starts off at 0, goes to 1/2, square root of 3 over 2, and then 1. So cosine of pi over 3 is 1/2. So this is 2 times 1/2. So x equals 1. Now we do our y. So y is r sine theta. So we do the same thing. It's 2 times sine of pi over 3. So it's 2 times the square root of 3 over 2. So y equals the square root of 3. So that point on the polar coordinate goes to 1 square root of 3. And because we're using sine and cosine that have that cycle, no matter which value of which angle I use, so if I went around the circle one more time and instead of having pi over 3 had 7 pi over 3, it still would come out to be 1 square root of 3 for my coordinate plane. So that doesn't make a difference in there. All right, so now the next one, we're going to go the other direction. So we have 1, -1, and I want to change that over to the r and the theta. So in this case, I've got x is 1 and y is -1. So let's look at my radius formula. So I'm going to simplify this a little bit and just put it as the square root. So I've got r equals 1 plus 1, which equals the square root of 2. So r is the square root of 2. And now I'm going to do my tangent of theta equals y over x, which is -1/1, which is just -1. And tangent of theta, when you get -1, ends up being 7 pi over 4. So actually, I'm going to take that back. It's going to be -pi over 4. Because remember, for tangent, your the domain, when you're looking at tangent to make it an angle, is -pi over 2 to pi over 2. So that's going to give you the whole function there. So on the tangent ones, when you get them, you're going to get that negative value. But if we're going to write our point, you can write it as a -pi over 4. Or you can write this as 7 pi over 4. You can write it either direction. So my radius is square root of 2. And I'll leave the -pi over 4. Because either one of those would actually work. So there's one other thing that we need to look at with tangents though. Which quadrant is one -1 in on the graph?
The fourth quadrant?
Right. My polar coordinates have got to be in the exact same spot. So if we're looking at this, because we're restricting tangent to -pi over 4, or from -pi over 2 to pi over 2, that's only looking at quadrants 1 and 4. So if my x and y were switched, so let's say I had this one. If I had -1, 1. If we looked at my radius, I would still get 1 plus 1, still is the square root of 2. The tangent of theta is still 1 over -1, which is -1. So theta still is -pi over 4. The problem is that's in my fourth quadrant, and -1, 1 is in my second quadrant. Okay. So we've got to pick a point that would work in the second quadrant.
Professor,
Yeah.
I was a little confused on how we ended up bounding theta between -pi over 2 and pi over 2.
Okay. So when you're looking at sine, cosine, and tangent, all three of those trig functions, because they keep repeating, if we're going the other direction, so if we're trying to take the arctan, arcsine, arccosine, they're not functions. So to make it a function so that we can go backwards, we have to restrict it. Sine and cosine, sine and tangent are restricted from -pi over 2 to pi over 2 when you're looking at those, because that gives you one rotation through every value that would work.
And,
So
and cosine is between -pi and pi?
nope, cosine is actually between 0 and pi. So if you think about, let's look at sine for a second. If I look at sine from 0 to pi or 0 to 2 pi, I'm going to get 2 times every single number that's in there. Because from 0 to pi over 2, I'm going up. And then from pi over 2 up to back to, or pi, I'm getting another set of those values that would work. So for sine, I'd either have to look from 0 to pi over 2, and then if I wanted the fourth quadrant, I could look at 3 pi over 2 to 2 pi. But if we shifted the other direction, we could look from pi over 2 to pi, negative pi over 2 to pi over 2, and we get one whole rotation of sine. And it's the same with tangent.
Okay.
That covers
And
the
so
code.
why do you have equals 7 pi over 4?
So remember that we were looking at the polar coordinates before. Remember how they rotate around?
Yes.
So if I went negative pi over 4, I'm over here.
So that's just another way to express it in positive terms?
Correct. Yep. If you wanted to express it in positive terms, it'd be 7 pi over 4.
But wait, do we have to?
No,
Okay,
that's why I wrote the point as negative pi over 4.
thank you.
No problem. And now this is where this actually comes into play, in all honesty, is that when we're looking at this, I've got that coordinate right there, and it's the exact same as the other coordinate I have. But those 2 points at the beginning didn't start off at the same. Remember when you take the square root of something, so this right here is r squared equals x squared plus y squared. When you take the square root of something, you have the positive and the negative version of that radius. So we have the positive version and the negative version. So to make this go to the second quadrant instead of the fourth quadrant, I'm just going to use the negative square root of 2. This way, I'm now in that second quadrant instead of the fourth quadrant. So the goal is to make sure that I'm in, that these 2 points have to be in the same quadrant. You don't have that problem going the other direction. You do in this one because you're taking the square root. All right. Let's look at some graphs. If I did, let's look at this. Go back to my graph. If I did x equals 5, I get a straight line, correct? If I did y equals 3, I also get a straight line. In essence, these are just, so these are the points assuming that the other one is 0. So what do you think would happen if I did r equals 2? What do you think I'm going to get? So let's go and look at my,
A circle?
you're going to get a circle. With a radius of 2, because that's basically saying my radius is 2, my theta can be anything. So you'll get a circle at that.
Sorry,
if
how do
I
you get
did-
Desmos to show you this graph?
If you go to your little wrench, right there.
Nice.
It'll actually do it on this graph. It'll do it on the coordinate plane or the regular one. It just looks nice when you do it on the polar graph.
Thanks.
If I did the other direction, if I had done theta equals 1, it's not going to let me graph that one. It's not going to let me graph theta. Why? If you did, so I don't know why it's not letting me graph theta. If you graph just theta, you actually get a line. Basically, it's a line that goes, and I'll copy it from the book since they don't have it. So you're going to get this. Because remember, basically what ends up happening, oh, I know why it's not graphing it. Let me do this. Nope, it's still not going to graph it. Oh, yeah. basically what you end up getting is a line that is hitting every radius, because radius can be anything, at that angle of 1. And then your radius is just the 2. So it's like you, anytime you do a radius, you're going to get it as a circle. All right. Let's look at some other graphs. I could show you how to do this all by hand. I am not going to show you how to do this by hand because I think you could. It's not that hard to do. You're just going to plug data or angles in. But I think it's actually cooler just to see how the graphs are looking. So r equals 1 plus sine theta. You can type in theta and it'll switch it to that. Or if you look down here, it is right there. If you click on the calculator screen, the ABC, theta is right there. So you can just use that button as well. All right, this graph right here. What does this graph look like?
You make me say it.
Sure, go ahead.
It looks like a butt.
Very good. Yeah, it's a heart. Don't ask. I look at it, I see a butt. However, when they first actually did this, the first person to graph this out and look at it goes, oh, this looks like a heart. It doesn't look like a heart to me. So this actually has a very special name. This is known as a cardioid because of heart. So the reason I'm showing you that one is because this one actually comes up quite a bit, and do you remember the cycloid? How I said that one comes up and is used. The cardioid also comes up and is used for it. So it's spelled like this. So that's cardioid. Yeah, I never saw a heart in them either, but yeah. So that's what the cardioid looks like. So we're going to actually do some calculations with it in a little bit too. All right, let's look at the other one. This is where I think the so we've got this. That's from 0 to, and I can look at where I'm going from. So I'm going to do this from 0 to 2 pi. It gives me, wait, that's why. There we go. I'm like, what did I screw up? So there's 0 to 2 pi, and you get leaves. If I went up to 4 pi, you're not actually getting anything. It's just going to draw over it more. But if you wanted different numbers of leaves, you can change that number there. So all the even ones will give you twice the number of leaves you have. So like if I did 6 pi or 6 theta, I have 12 leaves. If I do 7, I have 7 leaves. So the even ones give you twice as much. The odd ones give you exactly the same number. Because the odd ones, if we look right here, so I change that from pi to 2 pi, they're just on top of each other. So you technically have 14 of them there, but they're on top of each other. Where if you look at the 6 pi one, if I get rid of that, you lose half of them. Because it fills in the other half. So that if you were ever in school and playing around with a graphic calculator and want to know how to draw flowers, you use polar coordinates, and it draws nice flowers. Oh, I probably should do the 2 pi one. Since I'm going to put it in the notes. And you can do crazy things like there's, no matter how, well, when you're doing these, you can graph pretty much any type of thing you want in there. So like, here's a cool example.
So what's the application of these?
It's a different, well, this, there isn't an application for it. This is just fun. But in all honesty, when you're looking at these type of graphs, it's just a different coordinate system. So we look at navigation. You typically don't look at an X, Y coordinate system. You look at distance and bearing, and your bearing is a compass direction, which is basically an angle. So there is different application or different use cases out there. If you ever look at a radar system, it's typically circular like this, because it's in essence a polar coordinate system. So not everything uses X and Y coordinates. There are other things that we use for this. So this is just cool. But the actual polar coordinate system actually does have a lot of use cases. It also, another thing that it does is it gives us the ability to graph shapes that go over, like, that are not actually functions on the coordinate plane. They are kind of functions here, because every theta value gives you one answer. So while that cardioid looked funny, that's a function. Where if I graph that on the XY plane and it looked like that, that wouldn't be a function because my X has multiple values. Where in this, every theta only has one value. So that's actually a function.
So if you take and switch your graphs now, will it show us what it looks like on the Cartesian plane?
No, it'll just put that on the Cartesian plane, because I'd have to change it to the X coordinate, like I'd have to do the conversion over to the XY.
Oh, okay.
So whenever you type in R equals, it's just like Y equals. It knows that's polar, and it's graphing it as polar. So that's why when I'm graphing polar, I'll typically put it here, because I don't want you to think, oh, those are XY coordinates, because they're not actually. So. All right, fun's over. Now we got to do calculus. So before I go into calculus, if you're one of those ones that actually likes seeing cool and interesting and different things in math, polar coordinates is really kind of cool, but you also can look at hyperbolic geometry. And there's actually a theorem that how many degrees are in a triangle? Anybody remember?
180.
Correct. In hyperbolic geometry, I can have a triangle with 0 degrees. Which and honestly makes no sense. However, if you drew a triangle on a globe, first of all, I wouldn't have straight lines, they'd curve. And they could actually come to points where there's 0 degrees between those two lines. So it's looking at like basically drawing triangles and stuff on like a sphere. So there's really cool directions of math. Now, is it practical when they were originally looking at it? No, but when you start to look at it and putting it on a globe or a sphere, then you can start to see the actual connections to it. It's actually one of the reasons, if you ever look at planes paths, they never actually go in straight lines between the places. It's always curved. And it actually has to deal with fuel calculations and everything else, drawing lines on an actual sphere. They're technically going straight, but it doesn't look straight because it's going on a globe.
This is the whole concept about like two-dimensional or three-dimensional perspective in a 2D world and stuff like that.
Exactly. Yep.
Okay.
So that's what I'm saying. It's like we look at these things here. It's like where's the connection? It's like, but there is. You have to change your perspective sometimes. And yeah, going from a 2D to a 3D plane does definitely change how things look.
Because this
All
is
right.
this-
Yeah,
oh,
go ahead.
sorry.
Go ahead.
This is the whole concept of like once we figure out how like 4D works, we can work in a 4D world and a 3D world, and then we can change how like speed and distance work or something like that. This way
Yes.
further, but that's I remember reading about it.
Yeah, if you there's actually a book called Flatland that actually deals with all this. It's kind of cool. It's like actually a two-dimensional world that's invaded by a three-dimensional being. And it's like, how does it look? And it like the perspective and stuff. So it's like we have a very set perspective because we live in a three-dimensional world. But if you start looking at higher dimensions, like how is that going to change things? Because they exist, we just don't know how to work in them yet. All right, back to less fun stuff. Back to the calculus. All right, so we're going to find for our polar coordinates 3 things. We're going to find tangents. We're going to find arc length. And we're going to find area. Those are the 3 things we're going to look for. So the first thing we're going to look for is tangents. Now, this is my formula for it. So in essence, it's this right here. So what you're going to do is it's the end part that you need. So really my dy dx equals that. So you can kind of ignore the middle piece because we need that extra sine thetas and stuff like that in it, because in essence they're changing that dy d theta because we don't know what y is to my dr, and that's the actual calculations of it. So that's going to give me my tangents. All right, so we're going to look at our cardioid, and we're going to find tangent lines and where we have tangent lines that are horizontal or vertical. So the first thing is we need the formula. We've got dr d theta sine theta or cosine theta over dr theta cosine theta minus r sine theta. So we have to find the derivative of 1 plus sine theta. So that's r, I need dr. So 1 plus sine theta, the derivative of that's going to be cosine of theta. So I have cosine of theta, sine theta, plus 1 plus sine theta, cosine theta, all over cosine theta minus 1 plus sine theta, sine theta.
Super lost here, Professor. Where are you getting these from?
All right, so that's my tangent. So that's basically to take the derivative of that to find my tangents. That's what I need to use. Okay. So the first thing I have to do is find my drd theta, which is just the derivative of 1 plus sine theta. So I did this part up here. So that's cosine theta. So that's that one, and that's that one. And then R is the 1 plus sine theta.
And wait, how do we figure that the derivative of r is 1 plus sine theta?
No, R is 1 plus sine theta.
Oh, I
The
see.
derivative of it is cosine theta.
Got it.
All right, so we can simplify this down a little bit. So I can take out a cosine here. And then I have on the top, and I have 1 plus 2 sine theta left on top. And on the bottom, I have cosine squared theta minus 1 minus sine squared theta. Oh, sorry, not minus 1. Cosine squared theta minus sine theta minus sine squared theta. And I'm going to change this into 1 minus sine squared theta. So I have on the top cosine theta 1 plus 2 sine theta over 1 minus sine theta minus 2 sine squared theta. We got it broken down into that. And honestly, the only reason to break it down and simplify it down is to make our calculations a little bit easier when we're doing plugging in values to it. So I want to know the slope of the tangent line when theta is pi over 3. And I know my slope is cosine theta, sine theta over.
Different screen.
I'm just rewriting it on a different screen, but I was rewriting as I was reading the problem. So we've got pi or theta is pi over 3, and we've got my slope there. Now I just got to plug in pi over 3 to find out what the slope is at that point. So let's plug it in. We've got cosine of pi or pi over 3. So cosine of pi over 3 was 1/2. And then 1 plus 2. And then sine of square root of 3 or pi over 3 is square root of 3 over 2. 1 minus square root of 3 over 2 minus 2 times square root of 3 over 2 squared. So we've got 1/2, 1 plus the square root of 3 over 1 minus the square root of 3 over 2 minus 3/4. 3, 4, no, 3 over 2. All right. So we've got how can I put all this together? One plus square root of 3 over 2 over 2 minus square root of 3 minus 3. Oh, actually, I can put those together. This is negative 1/2. Negative 1 minus square root of 3 over 2. So this ends up coming out to be 1 plus the square root of 3 over negative 1 plus the square root of 3 equals negative 1. So the slope at that point of my tangent line is negative 1. That makes sense? That's a lot better than my writing. All right, so here's my cardioid. And we can see here on that point right there, that line, that's my negative 1 slope. So it kind of makes sense. The next part of the problem they wanted you to do was to find values that are going to make this have either horizontal or vertical tangents. Now remember, when you're doing horizontal and vertical tangents, we're looking at either the top being 0 or the bottom being 0. Remember, with trig functions, they consistently repeat on each other. So if we're looking for the top to be 0, that's the cosine theta 1 plus 2 sine theta equals 0. So the only times that's 0 is either when cosine of theta is 0. So cosine of theta is 0 at pi over 2 and 3 pi over 2. And then the 1 plus 2 sine theta equals 0. So I can bring this over. It's where sine of theta equals negative 1/2. So that's where theta is 7 pi over 6 and 11 pi over 6. So now if you look, that's that one, and that. The 3 pi over 2 is actually right here. And we'll talk about, if you notice that one right here is actually in both. So it can't be both a horizontal and a vertical asymptote, because that would end up being 0 over 0. So that point actually does not have an actual asymptote. So we have our vertical asymptotes at the 5 pi over 6 and the pi over 6.
Sorry, Professor, a little unclear on how to get the bottom two at 1/2 and -1/2. Are we just saying that because of the square root aspect of it?
Which part?
There's two horizontal lines at 1/2 7 pi over 6 and 1/2 11 pi over 6.
Oh, so okay.
Yeah.
So the 7 pi over 6 and 11 pi over 6 are just those are the thetas. If you plugged those in, the radius of those points would be 1/2. Remember, that's the radius and that's the theta.
Okay.
So from this point to that point, my radius is 1/2 in both directions. They weren't, so it wasn't, they didn't solve this. They just took those, you could take those points and plug them back into the R equals 1 plus sine theta. So if you plugged in 7 pi over 6 to that, so pi or sine of 7 pi over 6 is off the top of my head, I don't know. Unit circle. So sine of 7 pi over 6 is -1/2. So 1 minus 1/2 is 1/2. And that gives you your R. That's how they got those other, the 1/2s. Does that make sense? You got to remember, this isn't on the XY coordinate. These are R's and thetas. All right. Next, area. So if you remember, way back when you took geometry class, one of the things you were shown how to do was to find the area of a sector. It was probably later on after they talked about circles and stuff like that. They said, okay, if we cut this in pieces, how do we find an area of a sector? That's this formula right here. It's 1/2 R squared theta. That's going to give you the area of any sector on a circle. However, we need to be able to figure this out for any crazy shape. So the formula for that is it's an integral because we're going to be cutting it into pieces. So the integral from A to B, which is in terms of theta, so it's the theta start, theta end, of 1/2 the radius squared times d theta. So, but remember that R in this situation is going to be a function. It's not just a single number. Right. So let's use it to find the area of one of these leaves. So when we're looking at this, my area, I'm looking from negative pi over 4 to pi over 4. It's 1/2 the radius, which is cosine d theta. D theta. Oh, squared. Everybody understand where I got those pieces from? All right, so we're going to look at, so if you notice, to make my problem a little easier, it's symmetric. The top and the bottom are the same. So I'm going to pull out the 1/2 and I'm going to multiply by 2 and I'm going to cut this in half. So I only have to look at that part. So cosine squared of 2 theta. So the 1/2 I pulled out, and then the 2 is because I cut it in half. I'm only looking at half of it, so I have to double the area that I get. All right, so I can't do the integral of cosine squared, so I have to use the half angle formula for it. So it's 1/2, and it's 1 plus cosine 4 theta. Now we can do the integral of that. So area equals 1/2 theta plus 1/4 sine 4 theta. And we're evaluating it from 0 to pi over 4. So the nice thing is the 0 is going to cancel itself out, so I don't have to worry about the 0 part. So I've got 1/2 times pi over 4, and sine of pi is actually also 0. So this ends up being just pi over 8 is my area. All right. We got one more that we're going to do. So arc length. So this just proves this formula here, so you do not have to write all this down. If you want to look at how it goes through and come up with this, that's what this is doing. So the arc length formula is the integral from a to b of the square root of r squared plus the derivative squared. See that? So it's very similar to the formula that we were using for the arc length in the previous ones. in the regular one or the parametric one. So it's not much different in the concept of it. All right, last problem. Let's use this. So we're going to find the length of the cardioid. So my R is 1 plus sine theta. And then my dr d theta is cosine theta. So we're going from 0 to 2 pi. 1 plus sine theta squared plus cosine theta squared d theta. So if I do the 1 plus sine theta squared, I get 1 plus 2 sine theta plus sine squared theta. And if I add it to the cosine theta, that's sine squared theta plus cosine squared theta. That part right there is just 1. So I've got 2 plus 2 sine theta d theta. So this integral is not that simple to do. You actually have to rationalize it. So it's actually just as easy just to use a calculator to do it. So remember, you can use Desmos graphing calculator to do integrals. We're going from 0 to 2 pi. And we're doing the square root of 2 plus 2 sine theta d theta. So the answer is 8. So you can now tell your significant other that you have successfully figured out the arc length of a human butt to be 8. No matter how big you are, it is only 8 inches big. I'll be able to fit into your pants now. All right. That's it. So we've done parametric and we've done polar. You're probably, so the test for chapter 10 and 12 is in 2 weeks. It's going to be probably split half and half. So you're going to have half from chapter 10, half from chapter 12. So I'm literally looking at probably a arc length of each type, parametric and polar, an area of each one, parametric and polar, and a tangent of one of them. I'm probably just going to do tangent of the parametric one because I think it's easier in the long run. So that's the 5 questions you're going to see from chapter 10. So, and then chapter 12, we're going into vectors. So, any questions? As I said before, this class was the other one. So if you look on my website, there are actual videos for each individual section. So You have the video for 10.1, 10.2, 10.3, and 10.4. They're all just YouTube videos. You click on them, goes right up to YouTube, and they're not that long. So if you're looking for, if you're not sure on specifically a section, you can pull that up and watch those little videos as well. If there are no questions, have a wonderful night, and I will see you on Thursday.
Thank you, Professor.
You're welcome.